Good afternoon, everyone. It's a great pleasure today to have a visiting professor with us, Piotre Kolenderski. He's a professor at Toruń University in Poland, where he's also from. And Piotre, after completing his PhD in Poland, he actually came to IQC in Waterloo for 3 years of postdoc on an international scholarship. And ever since, we've been collaborating with each other on various projects on quantum optics and quantum entanglement. Piotre is now very busy setting up his lab, or has established a big lab in Toruń University, as well as also some commercial activities and various endeavors. So there's a lot happening. And it's a great pleasure to have Piotre here today and to talk to us about entanglement-based QKD and under daylight conditions. Thank you very much.
If we can remove the list, the participant list, you will try that.
Which is moving to the side, yeah, that's awesome.
Good.
That's like
that's okay on the top, just that goes away.
All right. Awesome. Okay, so hello everyone. So I'm representing actually two entities. One is Nicolaus Copernicus University in Toruń, and the other one is Entanglement, which is a spin-off company of Nicolaus Copernicus University. And actually, the full title of my talk is two words: entanglement-based QKD daylight conditions, and we'll why two words. Okay, so we are located here. This is Central Europe, Central Poland, where the university and company is. Yeah, I'm a leader of a single photon applications laboratory. So this is a group, a couple of people, and we work both at the university and also in the company. So we have a couple of senior researchers, students. At this moment, we don't have any student, and we have project managers. Project managers are the most important thing. So our group, so the rest work at home. Okay, so what are the subjects? Well, what are the topics that we work on? So there is a couple of things that emerged from our pure research, and now we are in the process of commercialization. And there are also some products that are already commercialized and we are selling. So one of the things is optical ground stations for optical communication. There is also a project by European Space, which we got from European Space Agency. I'm gonna talk about this project. This is cyber security of satellite links and QKD. We also have a small simulator for quantum information networks. And one of the projects resulted in, let's say, a way to measure distance between optical ground station and a satellite based on existing optical model. Okay, so this is the Department of Physics. Yeah, but first of all, this is Toruń. This is panorama of Poland from the other side of the river. This is the Department of Physics, and the Department of Physics we have this laboratory. This is one of them. This is the part in which we do prototyping of, let's say, things that we commercialize. So commercialization is a big thing these days. Okay, so we work at Faculty of Physics, Astronomy, and Applied Informatics. So astronomy is also mechanical stuff. Right? So astronomy is also a big thing in my department, in my university, because we have this 32 meters diameter radio telescope, which was already used for a couple of actually on the daily basis. They are looking at lasers and so on, and exotic things out there. But The telescope was used in, I think, 2002 or maybe 2000, for the exact date. For Cassini mission, there was Cassini mission, and they had a Huygens lander, which landed on Titan, that is the moon of Saturn. And that telescope was used to actually measure, or let's say, to say what is the distance between the surface of that moon and that lander. And it was a part of the network. The accuracy was 1 meter. Long distance and accuracy 1 meter. And from the same, let's say, community which works at the astronomy center, there was a guy, Alexander Polstan, who actually discovered the first exoplanet. And on the daily basis, they also have a couple of optical telescopes here. Unfortunately, they cannot use them to full extent because there is lots of trees here. This is the longest park in Poland, so they cannot cut any trees, unfortunately.
But this looks very short, this park.
Yeah, as small as the youngest. So, okay. But the things are quite fun. So yeah, anyway, they have a couple of optical telescopes, which they use also for SSA and SST, which means the space awareness. Okay, so what do we do? We are mostly financed by European Space Agency. And this is one of the projects that we want to be a part of. But this is very nice one because this is this for the development of European communication technologies. So the project is called Hydra, so like high throughput optical network. And they divided the project and ESA to 3 pieces. They call that element. So the first element is actually led by Kepler. This is a company from Toronto. And there is, I think, 11 or 12 satellites in a constellation. They have optical links between them. And the idea is to have also optical ground stations. This is element number 3. To communicate for the laser communication to the ground station. The element 2 is actually geo satellite, which is going to have optical link between the geo satellites and also radio to classical, or let's say classical ground station. So the idea behind that is that this is commercial. So if someone else has a satellite, then there's a possibility to send data and you can communicate with your satellite and your ground station. The intention is to have this kind of service. My group won't be a part of it's a ground station community. We want to provide those ground stations. Okay, so also regarding my group, we have a couple of projects, mainly from the European Space Agency. We're going to talk about the first one, which is National Center for Satellite Quantum Communication. This is the oldest one. And this is very related to the KISAT mission. Because the original idea behind that is the KISAT mission. I'm going to also tell about its arranging using optical models. What else do we have here? We also have quantum key distribution higher detectors. So in one of those projects, we developed this kind of spark detector in collaboration with Piotre. Okay. There is also a project. Okay, so this one is SAS, and this one is European Union. Horizon Europe. which is very fundamental. So this is a quantum version of optical coherence tomography. So the typical optical coherence tomography, it's a classic version. It's great. They should be short laser pulses to our eyes, and then based on that, they perform the tomography, so they can visualize everything what is in our eye, and they can detect and energies. So it's a subset of all these that can affect our vision. And the quantum version use two photons from a space. We will send one photon to the object, and then we mix that photon and the other photon. And then based on conglomerate, so is familiar with, you can say something about some. We also have this kind of simulator for quantum information networks. It's related to another project that we could collaborate on Thomas. All right, and maybe this one. This one is to actually demonstrate the multidimensional QKD protocol, which is the last one. I'm gonna talk more about this one. This is the security assessment testing validation for innovative secure communication and quantum technologies. So this is in order to establish a lab which is gonna certify quantum technology, like devices, optical terminals. So it's also under umbrella. Okay, so the first one could be. All right, so the goal is to measure the distance between this guy and this guy. So ground station and etc. So how to do that? So there is a couple of ways of doing that. One is laser engine. So people shoot high energy pulses to satellite, and then some of them get back, not fast, but single photons, and then based on the time of arrival, they can say what was the distance, and based on the distance and the orientation of the optical telescope, they can say what are the parameters of the orbit. But if we have optical model which works at the satellite and which can transfer data from your ground station, then we can switch that model. Actually, 1 second, Trey, 1 second, and to the measurement mode, and we can measure with the precision of roughly 1 centimeter. So we did that. Actually, we're working on that project together with companies. One is out of Polska, and the other one from Poland, and the other one was microwave from Germany. And we, as a university, were the prime contractor for this. How does it work? This was implementation. So the implementation was very, very simple. So we have evaluation board for FPGA for ground station, another one for spacecraft. As a class cards both sides, and atmospheric turbulence like that simulator was actually implemented in fiber technology. So it means that we used electronic modulator to actually what's gonna happen with the setup. Because in the end, what one can see using a telescope is just the transmission. So then we could do the same. Yeah. Okay, so this one. And the oldest one. So we started this one in 2016 and built quite nice manner for actually two things. One was very big optical ground station. The other one was quantum communication module, which was related to key submission. So the quantum communication module was a success that I described. So the idea was to have optical ground station, which on daily basis was for mainly for SSA and SST. So monitoring what's flying over our heads during orbits. There was two contractors, one was National Numerical Astronomical Center, Warsaw, and the other one was Kolenderski University in Poland. And for example, of the set, okay, but what works at this moment, since many years, is why optical ground station for 1 meter with telescope of 1 meter, which is located in South Africa. So with automatic robotic telescope, daily basis provides image many different satellites. And the quantum communication module, which I was responsible, my group was responsible for, it's a SPDC source. Yeah, so this is SPDC source, it's SPDC. You have non-linear stuff, you might have a strong laser, and then you have actually most of the nice cool different stuff, but some photons like 10⁻⁻⁻, the probability of this process is converted into it took 1 minute to have to open shutter. 1 minute, so very 20 years ago. So the process is simple. We have a nominal star, we have a photon. As I mentioned, is that 10⁻⁻⁻ probability. We have two photons at the output of as usually quantum communication is involved to do some those photons. Okay, what is the geometry of our setup? So the most important part is this one, is the non-linear stuff, and some paper. We don't have any corporate plates or photon plates as a wave plate side of the seminar group. Instead of that, first periscope, which actually rotates the polarization and it's not sensitive for the waving. So start with the classical pump, which is like the 532 nanometers, so very cheap laser and very available. We have a physics laser, which actually speeds the beam flow, which then goes and then we have another piece of so another physics laser to actually get those two beams together. And then we have one photon at 785 nanometers and the other photon at 1651. Yeah, so the question probably is why not and this is the process as well. Because one wants this is 5.1 or something. And yeah, there is a paper by Thomas and Paul, in which they so this is similar. So they have two even crystals in the roof. As far as I remember, that was 5.1, right? Because laser, but geometry is similar. And then the authors showed that the one photon is nice in telecom, band, not that far hours, and the other one is like 7 meters. Okay, and for our source, what was very nice and what made me very happy was that we estimated the bandwidth of the photon at 785 less than 0.04 nanometers. At the beginning, looked at the bandwidth, but then it turned out that this is the resolution of our spectrometer, so we couldn't measure actually the bandwidth that the source generates. But yeah, so this is that was one thing that made me happy. But the other one was that 2023, so 2 years ago, that was the brightest source as compared to the other sources for the virtual observers. More than 6 megahertz per second per milliwatt. And at the same time, those say entanglement parameters were quite nice. So that the concurrency or about 94%. And this is what I mentioned. Source can be tunable and also generate this configuration we have with another laser. Yeah, so stable shows comparison between the other sources. Yeah, I can get back here. But notice that those parameters, the fidelity concurrence is not perfect. There is a room for improvement because we actually designed and revealed set up based on components that we had in our lab at that moment. So, for example, there were these lasers, these calcite crystals, they were not, let's say, designed to cut the length of them was not adjusted for let's say the play of the geometry that we needed. So that's why there is a little bit of let's say misalignment of lack of the overlap, because for the perfect case those two beams they should overlap very nicely. Like the centers of those beams and also the width of those beams should be nicely aligned. And here, like geometry, there is a little bit of actually the alignment is not perfect. Would perfect have a little bit longer beam spacer, or we have another crystal to compensate for that. Yeah, so this is okay. So the next step was to demonstrate that we can perform, say, random distribution, and we can distribute one photon free space. So this is the drawing. This is our source. This is, say, a part of the experiment which allows us to attenuate. So we want to actually emulate what the conditions in real life, the optical. So we have like the attenuated for 700. We have a homemade Hubble telescope, and we have a telescope which was 10-inch diameter. And behind that telescope, we have a very simple polarization amount. So the distance between these two guys was of the order of 5 meters, because that was the space that we had in the lab. So that it was state of the group. Okay, so that was a hybrid. So this is space, 785, and the other photon can travel fiber speed of 10 kilometers. So 5 meters, 5 meters, 10 meters, 20%. It's found in this as analysis. Also creating and still conduct detectors, and for this one we used speak out to red bars answer. But the previous version of the Excelicons called 39. So I was really happy that it's 5 years. 10 years old, still work. Yeah, so this is the telescope. So it's okay, and we said the attenuation here for around 40 dB. So if the attenuation is such, then those are the parameters of the that we have. So we observed around 2.5 kilohertz of detections at 785 nanometers, and the total noise was of the same order. So we said such that we have signal to noise ratio of 1. So very wide, that's this approach. But even though those parameters are set, then show that we can get 15 hertz of row key, Q bar of 10%. Then those parameters are such. Okay, so this is all experimental, and we were thinking about whether it's possible or not use that kind of source or similar to have daylight communication. So we performed a couple of simulation runs for very low Earth orbit. So this one is extremely low. This one is low one, but not so extreme. All right. So what is that law? So it's secret key generation, right? Hertz. And this is the pump power. The pump power will explode. It's the power of hyper laser measured. So then you can see that you can generate output for some 16 months ago for, let's say, this output of 300 kilometers. And yeah, there is flashlight, and so the third one is optimized. So it means that we optimized over the bandwidth and constantly because the that we have right now is 0.35 millimeters. Actually, that's not, and that, but the upper bound. And for instance, low of 150 microseconds. All right, so this simulation proved that we can still see some counts, and we can still extract some. But yeah, so this is the simulation. And you said it would be, let's say, confirmed with the experimental data we have from simulation. Okay, so we work with horizontal. So we also try to do something more about the so we commercialized that thing. And now it looks like it's wonderful. We have electrons for this is receiver and some electrons for transceiver. Yeah, it's called rock duration. How does it work? So yeah, so this is a module which is ready to decide the direction of so the design is very simple. stage, there is a detector, quad detector, quad. So quad detector is 4 detectors together based on the position of the beam. So it's a beam authorized. There's no other. So the first and the simplest term of magic. Okay, so this is the loop and the yeah, so this week. Okay, where we are in this project. So we also developed for our customer a simple transmitter can transmit pulses and can transmit some data. But so it's like for model. Because our customer, which is HUH University of Technology, they have a project which is called Puchacz mission. Puchacz in Polish means owl. The satellite is called owl, has arms to shoot lasers that yeah, so the thing is that for testing of the technique, they're going to use the groups. There is birth, which means the demonstration, which we can now good. And we're going to use this for testing the real transmitters. So, transmitter. Make your works, but measurement comes your code. Okay, so at this moment, we also provided them with Polygon station. So this is Polygon station satellite what we provide light, the satellite is fiber. On top of Polygon station, other coordinated side, and show that you can transmit data in real time.
So if this one moves, this transition.
Not this coming.
Oh.
Yeah, so we use that for when we go for a conference in our books. We like that. Touch it, program stage. Sometimes they touch us. So. Okay, so this is the scene, and this is yeah, part of our program station. So at this moment we have this telescope with centimeters diameter and terminal. Everything is from plane wave. So we buy this part and we provide the back end for optical communication. And it's gonna be mounted on the pole, which is gonna be mounted in Poland. So this is for the same. Okay, and the last one, this is towards certification of QKD technology or general one technology. And it's also financed by the Green Space Agency, which likes quantum technology a lot. There's we can, for example, mention look at one of our projects, which we provided very fancy photon source. So the source actually split. We provided two couplers, there's step motors, also motorized coupler plates and with our plates, and also with temperature control, and also that these sources. So our partner, our Polska, they use this kind of source for the electronics to control all this source. So they wanted to provide the test bed for the electronics. So the electronics communicate with results, the photos, those photos. We turn on the laser and put some test temperature relation. What the people that was on this, let's say, a prototype. Then they moved to automotive grade.
You see in the middle, that's a source of entanglement? Okay.
This is just 2 ppm crystals in the Martian. This is actually for all the whole.
Oh, yeah, okay.
Okay. Yeah, so electronics work. As at the beginning, in 2018, there was Lisa had that idea to put a source on geo satellite. So that actually sustain those conditions of geo orbit. Okay, how do we validate? What's our approach to for the certification? So there is lots of side channels that one can imagine, which are there in practice. So there is lots of things that need to be checked in order to say that something is safe. So typically, we want to certify and validate whether this is useful. We should actually check quantum state fidelity, time, currents, the purity. So those are the parameters that I will describe. There is random number generator, and there are some tests that that random number generator must and there is many more that so for these we have the almost there. We have the apparatus and methods of testing of all that stuff. So there's like 200 pages of all the methods to go through in order to have the device to say that the device is safe or not. Okay, just in time. So this is my last slide. This is my group, actually half of my group, and we will work both at university and also in a company because we have project and actually assigned certain projects, and we have a couple of openings for postdoc, engineer, PhD folks. Actually, I didn't mention that, but a couple of co-students who will be able to also if someone is interested, there's going to be job offer posted also at SFU at some point. Okay, thank you very much.
Okay, thank you. Thanks, Piotre. So that's nice. We have some time for questions.
Hands up in the audience.
Yeah. Maybe now we can bring back the audience members list. So I'll just start. When you describe this entanglement with daylight conditions, right? You had certain assumptions on altitude and timing window and so on. Was that based on? Were those based on sort of real planned missions, or at the moment, or was it just based on sort of?
We just checked what is possible.
What is possible? Yeah. Okay. Yeah, because keyset will be a slightly different parameter range.
Yeah.
Okay. Yeah.
So for
keyset would be different. Yeah, you might have a different noise level.
Yeah, much higher.
Yeah. Okay. Yeah.
There's this one just The broadest filter is 1 nanometer.
Yes. And also the timing window is very, yeah, it will be a bit wider in key sets. 25. Yeah,
So maybe I think it was just 1 or 2 slides before this, you talked about your in-lab free space test and you set the noise level to be the same so that you would have an SNR1. Could you talk a little about what kind of noise you added to the system?
Those were just, let's say, dark counts plus trailer. So just
Okay.
Counts.
so you have a box here, it says noise simulator. What's in, I think that was the question.
Yeah.
What is that?
Just the laser of the wafer. So it will be.
Oh, I see. So your noise was a laser, very similar wavelengths,
Yeah, just to match the.
and you carefully tune the power that you have. Okay.
Okay.
Because I was also wondering about the geometry because, oh, sorry,
No, please.
because here you show the telescope, but we said it's only a few meters between them. And the transmitter is, how big was it? Is it? So I guess what I'm asking was, were those beams, they were not parallel, right? But the transmitted beam, was it diverging?
Yeah, it was diverging. So those lenses were of the 1 inch.
Yeah,
So that was just don't know.
Yeah. Okay. Because the receiver looks like 20 centimeters or something, right?
Yeah. It's a proper
A
telescope.
proper telescope, yeah.
The other one was not proper.
Not Yeah, cool. Okay,
Maybe a quick follow-up question then. You have 40 dBs of loss. Is that mostly coming from the single mode fiber coupling, or were you also adding some sort of simulated turbulence?
No. There was almost no turbulence in the lab. We just set it such that we have these transmissions.
Okay.
Disconnected. Yeah.
Okay.
Not only in the free space. The parameters fibers, the nothing goes through. Look into account all the interfaces of the connectors. And we optimized.
So you showed your design for a transmitter, which included also the set of piezo mirror. Yeah, it looks very nice and compact. So what was that already tested on a fluctuating beam or like outdoors under turbulence? Not yet.
That's why
Yeah.
Just as I mentioned a couple of times, you also have the vertical model for the horizontal.
Yeah.
But it's gonna be tested next week.
For next week.
Yeah.
Yeah.
There's gonna be like 2 or 3.
Okay. Yeah. And is this for telecom wavelengths? Sorry.
Yeah, this is sort of the becomes my kind of
This construction on the right here, is that all gauge?
yeah, it's more.
But is there like a metal mount on it? How is the combined steering gear attached to the line with the cage?
We prefer that.
Okay.
It's technical.
It's 3D printed, you said.
Okay. Is that on the right there with the other mirror, is that also 3D printed? Something?
Almost everything.
What's that?
What's the,
And you showed at the end that you guys are working with those companies, you're working on space qualified version, right? We showed right at the end the space or near space qualified. Yeah, like this slide maybe. Yeah. Is there like already a plan of let's say this entangled source, how big it will be for space in the end? Or is it one of those modules we see on the right?
It's just different.
Okay.
Those modules are controlled. So
Yeah.
it's just the test bed. At that time, we didn't want to create something in space quite quick.
Okay.
So this moment, there is not enough, let's say, human resources and resources for doing something just like
Yeah. Okay.
And there is Europe, there is also already 5 or 7 polarization compatible sources, which are very close to space gray. Okay, signal stuff. Okay.
Yeah. Could you please put the slide before, I think, the one that,
Slide number 4.
wait, I guess like most those parts, as you increase the pump power, why does it go down? Sequence widths.
Yeah, because here you have multiple pair emission events, so then it ruins your entanglement. And then you don't have creeps for generating the key. So there's too much power, too many photons, too many pairs at the same time, and that's why it goes up. And it's too few and too many. So good. It's very cool. My point somewhere. Thank you for this question. I forgot to.
I was just going to ask about this acceleration. This is basically direct photon transmission. There is no repeater node. Okay.
You mentioned that there's a lot of interest in commercialization these days. But what's your competition in Europe? And is there an attempt to coordinate through some European network?
It's a good question. I would say that at this moment there is a couple of companies which develop their own technology, and ESA is kind of a coordinated because actually has those projects and those programs for developing certain technology. Then based on that, companies need to collaborate with each other. So this kind of coordination. Money, they want to order something from, let's say, private sector, and then we'll collaborate. So it's kind of coordination. Excuse me?
Does it work?
Oh yeah, yeah.
Okay.
There is competition, of course, but and there's lots of projects which are between Europe and Canada. Canada is associated state with ESA, and there are some projects with this kind of cooperation. Yeah, it's a good question.
There's a comment
Oh, there's online
message in the message list. I saw it. So,
maybe if you click on the screen share, it might show up. Oh, yeah. Okay. Yeah. Okay, so maybe we'll conclude at this point. I'll point out Piotre is here for the most of August, so he's here like on a mini sabbatical until the third week third week of August. So if you want to meet up with Piotre, I'm sure he's going to be very interested to meet up and discuss more. So yeah, with that, thank you very much, everyone, and thanks, Piotre.
and focus.
Dann wird noch jetzt klar.